Hello everyone, this is the literature review for ACE 591. I am Shihabuddin Ahamad and today I will discuss YOLO Object Detector and YOLO version 7, a state-of-the-art object detector. The outline of today's presentation will be YOLO, how YOLO works, challenges, background knowledge, YOLO network architecture, YOLO performance, YOLO version 7 architectural reforms, state-of-the-art performance comparison for YOLO version 7, and experiment. So what is YOLO? YOLO stands for You Only Look Once. As the name suggests, the algorithm requires only one single forward propagation through a neural network to detect objects. This means that the prediction in the entire image is done in a single algorithm run. The CNN is used to predict the various class probabilities and bounding box simultaneously. So for YOLO, if you feed an input image to the network, it will detect the class probability and bounding boxes simultaneously with a single run. YOLO algorithm uses three techniques, which is residual blocks, bounding box regression, and intersection over union. I'll be discussing this in detail as I go on. Let us start detecting example. Let us detect a beer from a picture. For example, this is a picture. I want to detect a beer from it. So I have some objectives. The first objective is that I want to know the presence of an object inside this image. So I want to know whether there is an object present in this image or not. Secondly, I want to know if an object is present, what class that object belongs to. Is it a bear, is it a cat, or is it a dog? And lastly, I want to know the position of this bear, which will be defined in terms of these bounding boxes. During our training, we'll first divide our pictures into several S by S grid boxes. So we have divided our pictures into, for example, in this way, we have divided our picture to S by S. Here the value of S is 12. For this, each grid box is known as anchor boxes. For each of these anchor boxes, we will assign a vector. This vector will be assigned to each of these boxes. At first, let us assume that we are doing binary classification. That is, we want to detect whether black bear is there or not. 1, there is bear. 0, it's not. So the vector assigned to these anchor boxes will be like this. So there are 6 elements in this vector. As you can see, this 4 one is pretty simple. This one is actually giving the information of the bounding box. The x, y is the center of the bounding box. W and h is the width and the height of the bounding box. Whereas this p vector gives us the confidentiality or probability that an object is present in this xy coordinate. And c is the classification probability of this black bear. For this grid, as we can see, the center is like 7 and 6, the width is 7 and the height is 7, and the probability that there is an object here is 100%, and as there is only one object, which is black bear, so it will be 1 for this one. But for this grid, as we can see, that it is telling that there is no object presence here. The presence of object is 0, so we can disregard the rest of these 5 vectors, 5 elements. What happens for categorical classification? Now, along with black bear, we want to introduce 5 new things here, which would be M, A, I, N, E. Now, as we can see, these 5 elements are pretty much same as previous one, where there is only change in this vector. We have 5 addition of this vector, and this 0, 0, 0, 0, 1, 0, it kind of looks like one hot vector, because it is. Now, for each of these boxes, as we can see, that this box will be defined with this 11 elements, So the shape of these boxes will be 12 by 12 and the depth will be 11 because of this 11 elements. So as we can see, for this one, the xy is like 3, 8, width is like 3, height is like 4, and the class probability of n is 1, rest of them are 0. Same case for this one, the class probability of beer is 1, other than everything is 0. There are few challenges faced during the implementation of the network. The first challenge will be that what happens if for a center coordinate there are more than one bounding box, or in other words, there are more than one object. As you can see, for this center coordinate, this is the center for this beer, and this is also the center for this m. What will happen then? So what we do here is that simply we just concatenate these two bounding boxes into one. So there was 11 for this beer and 11 for this m. We concatenate them together and make it like 11 by 2, which is in other words 22 in total. Then the shape of this image would be 12 by 12 by 22. Another challenge is that what will happen if the object predicts more than one bounding box for each classes. So here for this beer it has predicted like 3 bounding boxes with probability of 0.93, 0.83, 0.90. Taking the maximum probability for the bounding box is not a good idea. In that case, we will just choose these boxes and we will disregard the other 2 boxes. But visually as a human being, we can see this beer and this beer is different. So in other words, this is an object and this is also an object. So how can we make the computer understand this thing? So what we do is that we use a technique which is not intersection over union. So basically we take all these 3 bounding boxes like this and we measure their intersection and divide with their union. Now for this small beer, as we can see, there is no intersection with the other bounding box. So for this reason, the IOU for the smaller one will be 0. So the technique is that if you have IOU less than some threshold value, for example here for the smaller one is 0, in that case we can treat that this is a separate object. Whereas if you have IOU larger than some threshold value, then we will treat that these bounding boxes are just indicating one single object. Now for this reason, this blue and red bounding box, they have higher intersection than a threshold value. Then we can assume that there are only one object present. So we will just take the object with the highest probability. So for this reason, the final bounding box for this beer would be 0.93. Another challenge is that what will happen in cases of object with different size. Now as you can see, this bounding box for this person is larger than the bounding box for that person, which is very small. How can we solve this? We use this multi-scale prediction method, which is sometimes also known as non-maximum suppression. So what we do is that we divide these images into S by S grid by using we just downsample these images into using some kernel. For example, the input size is here is 256 by 256. If we use a 32 by 32 kernel, then we can downsample it by 8 anchor boxes. So in this situation, these anchor boxes will give attention to the larger object, whereas if we use smaller kernels like 8 by 8, then we can get 32 by 32 anchor boxes. This will give priority to the smaller object also. For example, for this box, as you can see that these 4 people are in a single box. As a result, it will be the network wouldn't be able to detect them as one object. But whereas you can see that these 4 people has got separate attention. So there is a probability the object will be able to detect this one. Before we dive into the YOLO network, we have to have some background knowledge, like the knowledge of CNN. residual block, skip connection, upsampling, mesh activation, leaky ReLU, intersection over union, and non-maximum suppression. So we are quite familiar with all of them. The mesh activation function is quite new. So the equation for this mesh activation function is this one, and the shape of the function looks like this. Let us dive into the YOLO architecture. YOLO has got different version, a lot of variety. So with different architecture, there are some differences from one version to another version. So this is one of the basic YOLO version 4, which is pretty much easy to understand. So it comprises of a backbone, a neck, and the head. Head is actually the input. The backbone is head is actually the output. Backbone is the network where the input goes in, and the neck is actually where the convolution, all the detection for the head is done. Now, as you can see, for this backbone, a darknet 53 is used, and the input size is 416 by 416. The input size can be anything as long as it is a multiple of 32. Why it has to be a multiple of 32, I'll discuss later. Then we can see there is a layer which is CBM layer. So it is nothing but a conv layer followed by a batch normalization and a mesh activation layer. What about this CBL? CBL is a convolutional layer followed by a batch normalization layer and a leaky ReLU layer. So there is CSP, which is actually a combination of CBM and some residual block also. And at last we get this 3 outputs. So usually we have 1 output, but in this case we have got 3 output. Why there is 3 output, I'll be discussing very soon. There is one thing that there is no pooling layer used in this network. Instead of max pooling or average pooling, it was just replaced by convolution. For example, 2 by 2 max pooling, we just convolute the whole kernels with a 2 by 2 kernels with a value of 1. Now let us discuss about these 3 outputs. As we can see, there are 3 outputs. If we zoom at this output, then we can see that the shape of this output is 52 by 52 by 255. So how this 52 by 52 came? Remember this method where we divided a m by m image into s by s downsample image, where using k by k kernel. Same thing happened here. So our input image was 416 by 416. We used a kernel of 8 by 8, which by m divided by k, which is just literally 52 by 52. So yeah, that's why it looks like 52 by 52. What about this 255? Remember this one where we calculated the value of this vector would be 11, the size. So there was 5 which is in general, and there is 6 for each classes. So yeah, so for the prediction probability for the center and for the width and height, the total number is 5. The network was trained on Coco dataset, which has 80 classes. That's why the number of classes is 80. Now for each of those anchor boxes in this network, it is assumed that there would be a maximum of 3 objects, probably 3 objects present in that one single anchor box. That's why the size of a bounding box might be 3. So if you plug this value, it just becomes 5 plus 80, 85 times 3, which is 255. So now as we have seen this one, we can just easily tell this one, because here the kernel size is 16 by 16. That's why it's 26 by 26. The kernel size is 32 by 32. That's why it's 13 by 13. Very simple. Now if you look at the performance of YOLO, there are a lot of YOLO versions. So if you just compare with the basic YOLO 4 versions and some modified YOLO 4 versions, then we can see that it is performing quite well in comparison with other network like efficient net and retina net. So this is from YOLO version 4 back in 2020. Now the state of the art YOLO detector is YOLO version 7. YOLO version 7 is one of the fastest and most accurate real-time object detection model for computer vision tasks. Basically, it is also trained on MS Coco dataset from scratch, and it has surpasses all of the other detectors in terms of speed, giving 5 frames per second to 160 frames per second, in terms of accuracy for faster detectors, giving accuracy of 56.8 AP, and also the cost of processing is reduced up to 50%. Now there are some modifications used in YOLO version 7 in perspective of its previous successor. So it has used extended efficient layer aggregation network as its backbone, or EELAN in short. It has used the model scaling and concatenation based model to derive different versions of YOLO version 7. So YOLO version 7 base, YOLO version 7 tiny, and other one was there. It has used some trainable bag of freebies. The author researched on different technique in keeping the memory allocation and the distance it takes gradient back to propagate in mind. The shorter the gradient, the powerful the network would be. At the end, the author has chosen the extended efficient layer aggregation network, or EELAN short, as the backbone of their architecture. Next, model scaling. The main purpose of model scaling is to adjust some attributes of the model and generate models of different scales to meet the needs of different interface speeds. For example, if you need higher speed, but you are okay with compromising with accuracy, then you might need you can go for a smaller model which might be faster to detect, but it will have less accuracy. Then the reparameterization of conv layer. The author studied on gradient flow propagation plans to analyze how reparameterized conv layer should be combined with different network. So there are the list of this network which the author worked on. RepConv without the identity connection is used to design in the architecture finally. Reparameterization technique involves averaging a set of model weights to create a robust model. Training identical model with different training data and average the rates of those training models, which is also known as module level ensemble, is used for this YOLO version 7. The next tactics was auxiliary head coarse to find. Basically, at the output layer, two different head is used. The head responsible for the final output is called lead head, and the head used to assist the training in the middle layers is named auxiliary head. The main concept is to add extra auxiliary head in the middle layer of the network and the shallow network weights with the assistant loss as guide. The author used a lead head prediction as guidance to generate coarse to fine hierarchy levels, which are used for auxiliary head and lead head learning respectively. This is a SOTA state-of-the-art comparison for YOLO version 7 with other networks, keeping the number of parameters, the flops, size of inputs, and the AP values in mind. We can see that compared to YOLO version 4, YOLO version 7 has 75% less parameters, 36% less computation, 1.5% higher AP. If you compare to other previous model, it will be seen that the number of parameter has been lessened, the computation is also lessened. Sometimes the AP is same, sometimes it has gone to higher, but in general the speed is increased in a lot. YOLO version 7 compared to other object detectors, like as we can see here, there is a 1200% faster increase in speed than in this case. In perspective of the FPS, or frame per second speed, as we can see that the maximum FPS that YOLO version 7 can achieve is 161 FPS, whereas compared to this dual swan T, which is 6.5 FPS, it can approximately give same AP, giving same AP, but the FPS rate would be 161 frame per second. This is a real experiment done on my laptop setup, so it's a very entry level setup. So if we run the detection, that we can see that for YOLO version 7 base model, it can detect with a speed of 13 frames per second on average, whereas YOLO version 7 Tiny, it can detect up to like 33 frames per second. So for the mobile GPU, the performance, the real-time object detection performance is very good for YOLO version 7. So if we plan to use object detection strategy in future, mostly for mobile devices, then YOLO version 7 is obviously one of the best choices we can have. With this few word, I would like to end my presentation. If you have any question, you can ask in QA. Thank you.